Hi, hello. Welcome to my next session in high school chemistry. In the first session, I have completed up to Dalton's theory. Okay. In this session, I'd like to give you the modern view of atom. Okay. Let us see what is modern view of atom. Okay. So, what is the thing I am going to discuss in this session is the modern view of atom. The modern view of atom. What is exactly atom? An atom is the smallest particle of an element. What is an atom? Atom is the smallest particle of an element. The simplest definition, and that still remains identity and the properties of element. For example, the smallest particle of the writing material in your pencil is a carbon atom. Pencil, nothing but lead, is actually a substance called graphite. What is a pencil? This contains lead. That is nothing but lead pencil. That is nothing but graphite. What I mean to say is nothing but the pencil lead is actually a substance called as graphite, and graphite is a form of an element called carbon. Graphite is a form of element called carbon. So carbon's element is nothing but graphite. It is a allotropic modification of carbon. The point is, an average atom is about 10 power minus 10 meters. 10 power minus 10 meters in diameter. So what is the diameter of the average atom? That is approximately 10 power minus 10 meters. You can also write this one as equals to 10 power minus 8 centimeters. Also called as an angstrom unit. One angstrom unit. Such a tiny size is difficult to visualize for us. That means if an average atom where the size is gain of a sand, the grain of a sand is there, a sand of your hair would be about 60 meters in diameter. Okay, so what is this entire analysis is? Atoms themselves are made up of even small particles. That means these subatomic particles are protons, neutrons and electrons. What are subatomic particles? Subatomic particles discussion came because atoms themselves made up of even smaller portion of particles, and those smaller portions of particles of atom are called as subatomic particles. That we are calling, they are said to be protons. They are said to be protons, neutrons and electrons. Protons, neutrons and electrons. What are protons? Protons and neutrons are clustered together to form a central core of the atom. So what are protons? Protons and neutrons forms central core. Central core of the atom. That is known as nucleus. That we will call it as nucleus. So what is nucleus? Where protons and neutrons are present in the atom, that is called as nucleus. For atom, the fast moving electrons. What are the fast moving electrons? These are fast moving. Electrons are fast moving. Electrons occupy the space that surrounds the nucleus. occupies the space that surrounds the nucleus, and that we will call it as an orbit. As the names imply, subatomic particles are associated with these subatomic particles are associated with electrical charges. Electrical charges, and we can understand what is electron. Electron and its charge is one negative charge, and a symbol of the electron is E minus, and we can also say its mass is 9.01 or 9.1 into 10 power minus 28 grams. Whereas if you take a proton, proton symbol is P and its charge is plus 1. This is proton, and where you can write P plus, it is 1.67 into 10 power minus 24 grams. In the case of neutrons, if you take neutrons, the charge is 0, and that is N is a symbol for each. N is a symbol for each, and its mass is almost approximately equal to see that of the proton, that is 10 power minus 27 grams. And coming to the point here, in this discussion, we would like to talk about a few things related to this radius of the electron, proton, and all these things. Smaller than 10 power minus 18 is electron. Electron size is smaller than 10 power minus 18 meters. So I am telling about this is the name, this is the charge, this is the symbol. Okay, this is the electron, this is proton, this I am writing as the name of this compound, element name, subatomic particle name, and I am writing here charge and writing the symbol of the subatomic particle, and here I am writing the mass of it. Here I am telling about the size of it. Okay, so this is a table form I am writing. When you come across the sizes of the protons and neutrons, it will be 10 power minus 15 meters, 10 power 15 meters approximately, please. That means what you learned in this one is a modern view of an atom. What is modern view of an atom? Atom is a very tiny particle, and but it is not that much tiny particle when compared to the size. Is very difficult to visualize an average atom where the size is of a grain of a sand, and a strand of your hair would be about 60 meters in diameter. So atoms themselves are made up of even smaller particles, and these subatomic particles we call as protons, neutrons, and electrons. Whereas the protons and neutrons cluster together to form a central core that is called as nucleus and of the atom. As the names imply, the subatomic particles are associated with the electrical charges, implying the subatomic particles are associated with the charges, and that we saw in this table form. And summarize the general features of the protons and properties of the atom here in this table I have summarized. Okay. What is the expression of the mass of subatomic particles? Here, as you learn in this table form, the subatomic particles are incredibly small. If you see this information, they're incredibly very small, and suppose you could count our protons and neutrons equals to like an Avogadro number, then put on a scale, then you would have a mass of about 1 gram. Then this mass of the proton and neutron has a mass of very very small value of 10 power minus 24 parameters will come. That I will show you here. Or is nothing much. For example, if you are taken the means of one proton and neutron has a mass of how many grams? For example, you have taken, this is the proton or neutron here. I have told you, that means when you suppose you would count the out of protons and neutrons equals to Avogadro number. That means proton number or neutron number equals to Avogadro number. So that Avogadro number of this protons and neutrons, put them on a scale, they would have a mass of about 1 gram. They would have a mass of about 1 gram. Then this means that one proton and neutron has a mass of, what is the mass of one proton or neutron? That will be 1 by Avogadro number. So 1 by Avogadro number, that is 1 by Avogadro number is 6.022 into 10 to the power 23. When you write it to the exact after calculation, then you will get 1.66 in 10 to the power minus 24 grams. So that means it is a convenient to measure the mass of subatomic particles using units such as grams. Instead, chemists are using this unit called as atomic mass unit. They are using atomic mass unit, the mass of the atoms, U. Instead, chemists use this atomic mass unit. A proton has a mass of about 1 unit and which is equals to 1.66 in 10 to the power minus 24 grams. So, you are telling the unit, then that is nothing but 1.6 in 10 to the power minus 24 grams. Right? So, this is the most important point to be understanding the expression, the mass of the subatomic particle. Next, I hope you understand the modern view of the atom in this discussion and its tabular form. Now, I would like to give you the concept of the nucleus of an atom. Concept of the nucleus of an atom. Dear students, the nucleus of an atom, the nucleus of an atom is the discussion we are doing now. As you know, all the atoms of a particular element have the same number of protons in the nucleus. For example, if you take an atom of the element will have the same number of protons in the nucleus. For example, if you take A is an atom of an element and B is an atom of another element. So it contains, there are X number of protons are there, and A is also another atom, assume A only, of another atom. A is another atom of the same element. So I am taking an element and the element contains the two atoms, and this atom also contains X number of protons. It's a very simple thing. That means what is the meaning of this one? All the atoms of a particular element have same number of protons in the nucleus. Right? For example, all the hydrogen atoms anywhere in the universe. What is that? All the hydrogen atoms anywhere in the universe have one proton. That is the meaning of it. Why? Because hydrogen atomic number is 1. We are telling 1. What is that 1? 1 is the number of protons in it. Like that, if you take helium, all the helium atoms have 2 protons in the nucleus. Like that, if you know oxygen, all the oxygen atoms have 8 protons in the nucleus. That means chemists use the term atomic number as a symbol for it. For example, if you take hydrogen, hydrogen contains how many protons? 1 proton in nucleus. When you take helium, it is having 2 protons in its nucleus. Like that of you take oxygen, then it contains 8 protons in its nucleus. In its nucleus. And this number telling Z is a symbol for atomic number, refers to the number of protons in the nucleus of an atom of the element. That means hydrogen element contains hydrogen atoms having 1 proton in the nucleus, and helium element is having helium atom contains 2 protons in their nucleus, and oxygen element contains oxygen atoms in the nucleus. They contain 8 protons. That is the meaning of it. That is putting its symbol Z. As you know, the nucleus of an atom also contains neutrons, not only protons. Nucleus of an atom also contains protons, right? In fact, the entire mass of the atom is due to the combined mass of the protons and neutrons, and therefore an element mass number is the total number of protons and neutrons. So, what about the mass number? Mass number, they given a symbol that is A, that is proton number plus neutron number in the atom, right? So a total number of protons and neutrons we will call is the atomic mass number, where if you take an example like oxygen atom, if you take, which has 8 protons are there, we discussed, that means it is having 8 neutrons in its nucleus, has the mass number 16. So oxygen mass number is 16. The 16 is nothing but it is having 8 protons and 8 neutrons in it. That's the meaning of it. A uranium atom if you take, is having 92 is the proton number for it, and they have identified that there are 146 neutrons are there. Then this total will become 238. That 238 we will call it as its mass number. So proton number and neutron number, total number is called as mass number of the atom. And moving on to further information about elements, protons and neutrons is often summarized using chemical notation, that you will see in a stable form. And the letter, you know that what is the letter? The letter, we will keep X is a symbol as a notation for the element, atomic symbol of an element, and atomic symbol is also called as element symbol, right? Each element has a different atomic symbol is there. All the chemists actually throughout the world use the same atomic symbols. Over the coming months, we will probably learn to recognize many of these symbols instantly. See the back of this book, then back of this discussion, there is a list of the elements you will discuss in alphabetical order along with the symbols. You can also find the elements on the symbols in the periodic table inside our books, right? So this is the symbol. In this symbol, the X you will put here and A you will put here, and even you must know the Z is a symbol here. You're right. So what is A here? A is the mass number. A is the mass number. What is the Z? Z is the atomic number. Z is the atomic number. What is X? X is the atomic symbol. X is the atomic symbol. Atomic symbol. Right? So notice that when a chemical notation in this type of picture we have drawn here, in this notation, it does not tell you about the structure of the elements of an atoms. For example, consider element fluorine. So how you write fluorine is 9F16 or 9F19 we will write, right? This is for oxygen clearly. Now in F19 we will write the mass number, that is superscript, indicates that fluorine has a total of 19 protons and neutrons, right? What is this one? The subscript. The subscript is telling that the 9 indicates that fluorine has 9 protons. This 9 indicates that 9 protons are there in the fluorine. Neither the mass number or atomic number tells you how many neutrons fluorine has. Right? That's why you can calculate the value, however, by subtracting the atomic number from the mass number. So how will you find the neutron number? Neutron number you will find by subtracting the atomic number from the mass number. That is A minus Z. So here what is A? A is the mass number and Z is the atomic number. Right? So this is the formula to calculate the mass number and atomic number. I will try to find what is neutron number. Neutron number is equals to atomic mass number is 19 minus Z, value is 9, that is 10. 10 is the neutron number. Okay. So this is the answer we calculated, that is for the neutron number of fluorine. So, okay, using this atomic number to infer the number of electrons, as just mentioned, atomic number, mass number do not give any kind of direct information about the number of neutrons of an element. So, they do not give you number of electrons, either you can infer the number of electrons, however, from the atomic number. So, what is atomic number? Atomic number is the number of electrons when the atom is neutral in state. And the atom of each element are electrically neutral, then that means the positive charges protons and negative charges electrons must balance each other. Then the neutral atom of any element, the number of protons is equal to the number of electrons. For example, neutral hydrogen atom if you take, then what will happen? It contains one proton, so it must also contains one electron. Whereas a neutral oxygen atom if you take, it contains 8 protons and it must contains 8 electrons. That is the using the numbers and the atomic numbers and mass numbers. So this is about mass numbers, and let us shall we move to the next one, that is isotopes and atomic mass. Isotopes and the atomic mass. Isotopes. Actually, all the neutral atoms of same element contain same number of protons and therefore the same number of electrons. So, electron number and proton number same for the neutral atoms. So, the number of neutrons can be varied. For example, most of the oxygen atoms in nature have 8 electrons in their atomic nuclei. In other words, most oxygen atoms have mass number 16. That we will write it as mass number is 16. This is. So, 8 protons and 8 neutrons. This is the case. As you can see, there are 2 neutrally occurring forms of oxygen. So one of these is has 9 neutrons are also there for oxygen. Oxygen 17. In that case, 9 neutrons they noticed and 8 protons they have noticed. As other they are having 10 neutrons also noticed for oxygen. So 10 neutrons and 8 protons are noticed in the oxygen case. That means these are the 3 forms of oxygen which are called as isotopes. Which are called as isotopes. Of an atom of element, they have atomic number is same. That is proton number, but different number of neutrons are there here. Neutron number is different. Neutron number is different. The proton number is same. That means 8, 8, 8. So Z value is same for this kind of elements that are called as isotopes. You got it? Right. So isotope is nothing but the set of atoms belongs to same element with a different neutron number or mass number. They are called as isotopes. The isotopes of element have very similar chemical properties. We can say these are all having the similar chemical properties because they have same number of protons and electrons. So electron number and proton number in this case is same. That's why their chemical property will be same. But they differ in the mass. However, because they have different number of neutrons are there, that's why mass number is different. And some isotopes are more unstable than others are also there. We have the different mass, however, because they have a different number of neutrons. And their nuclei, whatever is there, plural, that is nucleus. You can say nucleus, plural is nuclei, and are more likely to decay, releasing energy and subatomic particles. That is called as radioactivity. What is radioactivity? Something but decay. So I am telling the one thing, the most important, decay of the nuclei. Decay of nuclei of these elements naturally takes place, so that will call it as radioactivity. As happens actually spontaneously. But all the uranium isotopes are there, you can understand easily. They have unstable nuclei are there, definitely they will they undergo radioactivity. So unstable, whenever the atoms are unstable, isotopes are unstable, definitely they will undergo radioactivity. Uranium is the best example for this type of thing, that is uranium. U is nothing but uranium. Isotopes are there, they will undergo radioactivity because they are having unstable nucleus, isotopes, right? And many isotopes are not actually radioisotopes. Oxygen 3 naturally occurring isotopes are there. For example, they are all stable. In contrast, we have chemists have successfully synthesized 10 other isotopes of oxygen, all of which are unstable radioisotopes are there. And what products results when radioisotopes decay, and you will find out in the other chapter. So we know all these things we have from the data information we are finding here, we are writing. But oxygen, other 10 unstable radioisotopes also discussed in the science till now we have observed, right? Let us move to the next one. Electrons of atoms. Electrons of atoms. Electrons of atoms. I am going to tell you one thing about the electrons of atoms. That means, so far much of the discussion about the atom has concentrated on the nucleus and its protons and neutrons. And what about electrons? What about electrons and what is their importance in the atom? Recall, the electron occupy the space surrounding the nucleus. Therefore, they are the first subatomic particles that are likely to interact when an atom comes nearer to another atom. Right? When an atom comes nearer to another atom, which subatomic particle likely to interact is nothing but electron. In this way, electrons are on the front line of the atomic interactions. So, what are electrons? Electrons are in the front line of atomic interactions. Front line of the atomic interactions means they are most important subatomic particles leading to the chemical reactions. The number and arrangement of the electrons in the atom actually determine how the atom will react. So, how the atom will react depends on the number of electrons will be determined. So, number of electrons determine the reactivity of atom. That is most important point to be noticed here, and that means if at all with all the atoms, as you learn about the session, that throughout the rest of this unit's discussion, we have electrons are said to be responsible for the chemical properties of the element. So finally you can understand one thing, that electrons are responsible for the chemical reactivity. So what are electrons' importance? They are responsible for the chemical. They are responsible for the chemical reactivity. So this is the most important points regarding electrons. So what about the electrons cases, like neutron cases and proton cases we have discussed. On these electrons are playing a vital role in the discussion of atom and its reactivity. Revisiting some of the atomic theories, what will happen? Let us see. John Dalton in this discussion did not know about the subatomic particles when he developed this atomic theory. That is one point to be understand from the advanced theories. And even so, the modern atomic theory, whatever is showing that retains many of the Dalton's ideas and with only a few modifications. Examine the comments of the right of every discussion, whatever we are doing here, and they explain how the modern theory differs from the Dalton's theory. The atomic theory is a landmark actually achievement in the history of chemistry, and it has shaped the way that all the scientists, especially chemists, think about matter and all these things. In the next session we will see that one, and now we are going to discuss about the modern atomic theory to conclude this session, right? So the modern atomic theory, the modern atomic theory. Dear students, all the matter is made up of tiny particles. We told they are called atoms, and each atom is made up of smaller subatomic particles, protons, neutrons and electrons. That means all the matter made up of, all the matter is made up of tiny particles called atoms. And each atom is made up of smaller subatomic particles, electron, proton, neutron, right? And moving on to the another point in the modern atomic theories, we have the atoms of one element cannot be converted into atoms of any other element by chemical reaction. So that means atom of one element cannot be converted into atom of another element by a chemical reaction. That is one thing. What is another modern theory is telling that atoms of one element have same properties such as average, mass and size. These properties are different from the properties of atom of any other element. So, properties such as average, mass and size. Average, mass and size of an atom differs from other atom of different elements. Different elements. So this is one most common. This is considered already in the Dalton's theory. And atoms of different elements combines. That's what we told about the Dalton's theory. Atoms of different elements combine a specific proportion to form compounds. Atoms of different elements. Atoms of different elements combine in specific proportion to form compounds. How can we understand the first point? That means matter is made up of tiny particles called atoms. Each atom is made up of small subatomic particles like electrons, protons and neutrons. Although atom is divisible, it is still the smallest particle of element that has properties and identity of the element. The second one, atom of one element cannot be converted into atom of another element by a chemical reaction. For this, nuclear reactions are there. The changes that after the composition of atomic nucleus may impact convert atoms of one element into another atom. That is modern thing, that is nuclear reactions. The third one is the modern theory. The different atoms of element have different number of neutrons, right? So we discussed about isotopes. Different isotopes of element have different number of neutrons and thus different masses. As you will learn all these things in the next chapter about the neutron concepts and all these things, nuclear chemistry. And this entire idea of atom different from the elements combines to form compounds is as remained basically unchanged from the Dalton's theory, right? So this is about the modern atomic theory. So elements and periodic table. In the first we discussed about elements. In these two sessions, definitely we will discuss about the periodic table on its classifications in the next sessions. Until have a nice day. Bye bye. Dear students, please subscribe my channel if you want continuous classes like this. Thank you very much.